All right. Sorry for the delay. Welcome to our first building energy session at Modelica Conference 2022. My name is Kaustubh. I will be the session chair. There are three interesting topics in this session, and each presentation will have 15 minutes plus 5 minutes Q&A that will be followed. Please keep your phones on silent, and with that, I invite Fabienne. Fabienne will ask from Beyond Energy Research Center at RWTH University. He will be presenting the open source Modelica library best mode. Fabienne.
Yeah, thanks for the nice introduction, and I'm really glad that I can be here in the States to present the latest development from our institute in Aachen, the library BESMod, which provides building energy system modules. As I planned this speech for 20 minutes, I will still keep the same motivation as planned, but maybe go over some details a little bit faster. So if you're interested later in the library concepts, please ask me or my colleague Laura, who's also here, any questions. We developed the library with the goal in mind that we want to achieve climate change by installing new renewable systems and having a shift to more electrified energy systems. And to achieve this goal, we have to develop new control and design methods. And one tool to do this, which can aid as an economical and fast option, is simulation, because in here we can quickly analyze if a method is good or not before we actually have to build it and test it in the field. And when we want to simulate renewable energy systems, we actually have to consider different domains, because renewable energy systems, especially in the building energy sector, are intertwined. We have like control domain, hydraulic domain, building domain, electrical domain, ventilation, also user, domestic hot water, so everything interacts with each other. And when we want to evaluate a certain method, we really have to simulate them all together. And as you may know, Modelica enables the modeling and coupling of different domains. And this is why we looked at the existing pool of modeling libraries to check if there's one library which enables the modeling of coupled, domain-coupled building energy systems. And luckily, out of the over 100 open source libraries, there are in total 12 libraries focusing on building energy systems. Maybe you know some of them. If not, get to know them as an invitation. Most famous probably is the ibipsa library, which acts as a core library to 4 others. The ibipsa library adds different models for different domains. I'm just going to give some examples of the domain components the libraries share. So the ibipsa one has models for fluid systems, hydraulic and ventilation systems. The ideas from Belgium adds, for example, a thermozone model with a detailed building envelope. The building systems library from Berlin has a PV battery model. The XLIB from our library XLIB from our institute in Aachen also has a PV model and also an air handling unit model, for instance. And probably most famous is the buildings library from Berkeley, also probably the most well maintained. And they also have different models for different domains, detailed building models, really nice control models. And then outside of this ibipsa scope, we have other libraries as well. From Germany, we have one building control lab, which aims to provide control models which are really close to the practitioners. And we have the last year's Modelica Library Award winner from the DLR, the Thermofluid Stream Library, which acts or provides really detailed vapor compression models, which can then be used to analyze heat pumps in detail. And we have other libraries as well. So overall, a really rich pool of component model libraries. Now you may ask yourself, why did I invent a new library? Well, if we want to simulate multiple domains altogether, we can state that even though the libraries all have models from different domains, they not always have the best models. What does best model mean? It doesn't mean like well maintained. it means that it fits the research scope you have. So for different research questions, you need different models with different levels of detail. And out of these 12 libraries, we have, for example, 3 different PV models, all with different aspects. And depending on what you want to research, one of these models is maybe the best model for you. And to overcome the issue, we didn't want to implement a new library with a lot of new models. We just want to use all the existing libraries. And the other issue for building energy system simulation, these libraries focus heavily on components. There are some examples for system applications, but yeah, really coupled energy systems are not present. And this is mainly due to a lack of uniform interfaces and also consistent parameterization. And when we keep in mind that we want to use multiple libraries, this is even more important. And this is why we have to provide systems, modules, using a modular structure and consistent parameterization. And this is why we had the motivation to develop BESMod, the library presenting building energy system modules. We implemented BESMod with 2 key ideas in mind. First, we built BESMod upon different other libraries. We have 2 required libraries, which are the Modelica standard library and the Ellipsa core library, which provide interfaces and really basic models. And then we have optional dependencies. You don't have to install them, but you can install them using a dependency manager. And currently, in the current version, we have the buildings on the AXLib and the building systems as a dependency. This is mostly due to the fact that we are common with these libraries, but we are really happy to welcome any other library as an optional dependency as well in the future. And then the other part, we want to provide modules, and this is why we implemented BESMod in a fully modular way. So when you look at the package structure, you see that we don't add component models, but we only add basically containers for the different domains and provide typical subsystems or modules which can then be used later to combine to a complete energy system. How do we define modularity in Modelica? If you want to basically combine any module with another module, you don't always know beforehand which information is going to be exchanged. So for information exchange, we use expandable bus connectors, and we implement different bus connectors and we separate them using color coding, so it's always visual which one is being used. We have, for example, a building measurement bus, so with data from the building envelope, a control bus, a bus which collects all relevant outputs, which can then be used to for analyzation, and also, for example, the user profile bus for user set points. Really important, we never predefine variables in these expandable connectors, and we never use them on the uppermost level because this can lead to unwanted behavior and really nasty debugging, at least in Dialoga, or Modelica just doesn't translate at all. Then we use vector size ports. So between different modules, we always use arrays of fluids ports to enable the simulation of multiple zones or multiple hydraulic circuits which are parallel to each other. And each subsystem is replaceable, and this is implemented by using some partial module and the constraint by clause, and then the choices are matching so that the user at the end can select the module they want to use. Also, we use modifiers in the constraint by clause to set some parameters final, and this is going to be explained on the next slide and is related to our approach for consistent parameterization. We built BESMod with the idea of always having 4 types of parameters. So we have top-down parameters. These top-down parameters were shortly visual in the prior slide. They are given by another system and are always final. Then we have bottom-up parameters. These parameters are defined by a subsystem and can be calculated as given equations by the top-down parameters or the other remaining parameters. Then, as only a lot of libraries implement this already, we separate modeling and component physics by using records for component data And we also try to link the top-down parameters, which I'm going to explain in the following, to this component data. And lastly, we can fine-tune the layout of a subsystem by using component choices. So, for example, we could disable the bypass valve if we don't want to simulate it all the time using Booleans. How do these four parameters interact with each other? I'm going to explain this in this example. If we have a subsystem which contains the building envelope, we can calculate using the record data of the building physics and the bottom-up parameter of the nominal room temperature to calculate as a set equation the nominal heat flow rate. And this nominal heat flow rate is then used as a top-down parameter in other systems. So, for example, in the radiator system, and using the nominal heat flow rate and other record data, we can calculate the nominal mass flow rate, nominal pressure losses, and so forth. And we can then use these bottom-up parameters again and propagate them to other systems as top-down parameters. This approach using top-down and bottom-up parameters comes in really handy if you have a lot of systems and want to reduce at the end the effort and also error possibility of the user. So if you don't use this propagation, you will have or encounter more errors. Now coming from the approach of modularity and parameterization towards how a building energy system looks like in VESMod, we motivated the coupling of domains. So we want to simulate control domain, hydraulic domain, building domain, and so forth. So the system simulation of a building energy system always looks like this. So we have it doesn't work. We have the electrical subsystem and the building envelope, ventilation, hydraulic subsystem, control domain, domestic hot water, and user. All these domains interact with each other. And I'm going to explain in the following, for two examples only, because now I have limited time, on the choice of connectors, layout of the system, and parameterization, and start at the core of the system. For the building envelope, we define this module to only contain really the building physics, and we separated internal gains and user profiles to another module. And as different building model approaches use different methods of internal gains, these two modules are kind of intertwined, but that's another issue. For connectors, we have thermal heat exchange, we have ventilation of fluid ports, and also electrical ports. And for parameterization, this module only has bottom-up parameters, like the room temperature, nominal heat flow rate, as I've explained, and also the geometry, for example, of the roof to automatically size a PV system. Available modules in VESMod are currently the thermal zone model of the XZip library, the high-order model of the XZip library, and the mixed air model from Buildings. And in the next months, I'm planning to implement the Spawn of Energy Plus integration. Again, currently, definitely a shift because I'm from Aachen and we use heavily the XZip, but any other building envelope approach could be implemented as well. Then I'm going to explain the hydraulic system. The hydraulic system is not one system, but contains subsystems again, because the system structure of an energy system is pretty well defined, for example, in the European norm, or actually also in an ASHRAE standard, where you can separate a system in generation, distribution, transfer, and control of the system. And by separating these modules, we can define typical subsystems and then aggregate different subsystems to, again, unique building energy system. And for connectors, we have to use fluid for domestic hot water and heat transfer for the building. And for parameterization, we heavily rely on typical design rules. One design rule is actually already implemented in the BIPSA library. So, for example, you can calculate the diameter of a pipe based on a mass flow rate and a typical flow velocity. And this really simplifies the parameterization and also reduces errorness for the users. And we implemented such rules based on standards for all the subsystems in the hydraulic domain. Mainly because we are focused on hydraulics in Germany really heavily. And also this subsystem has most examples already. So we have heat pump, boilers, storages, controls, you name it. Also, for example, the model from the solar thermal system is not as good as the one from the buildings library. So here we used the buildings library as an optional dependency. I'm briefly going to go into detail on the electrical system because I have only 5 minutes left for the presentation. I only want to note that the layout stays the same and that we don't use current and voltage as an information because all component libraries currently use power as an information of the component, and we decided that it's not our job kind of to define which current or voltage is being applied by the components. This is something the component libraries have to implement, and we are happy to adapt the connectors we implemented. And also for parameterization, we have again some rules, and we use existing libraries like the building systems or the exit PD middle. Then the ventilation system is basically all the same. For weather data, we don't need replaceability because most tools already convert to the existing weather data reader in their Lipsa library. And we have a supervisory control, which enables a supervisory control, which is completely Modelica internal, and an external control, which could enable the coupling of BESMOD to Bob test. And you can just disable a supervisory control in each local control only. So this is also how it's done in reality. For simulation, you just redeclare everything, select your component records, choose a weather file, and hopefully simulate. And we also have options for debugging, so we can disable single subsystems, and we have test packages for each of these modules, so it's really handy to evaluate if an error is introduced in a module or in the aggregation of modules. Then we have a lot of different examples, also some publications already. For proof of concept, we chose a system which couples all domains and just simulated two different building approaches by defining one partial use case and then replacing basically only the building envelope, and everything else stays the same. To simulate, we only use graphical interaction. We don't have to connect anything on the top level, and the annual simulations take less than 6 minutes. The results are not that important. They're different building physics, different buildings in total. It's just interesting to see that the different domains interact with each other, and you can read the paper because my time is sadly running out. I really want to go quickly into detail on the current or future aspects. We want to validate it. I have a new project with 8 real buildings where I have the chance to do this. We want to increase the compatibility to Open Modelica and extend the already existing continuous integration, and then achieve the goal of develop new design and control methods by interacting also heavily with the control domain. Maybe we can talk about a new Bob test case, and we also have already coupling to ontologies such as BRIC. Last, I want to highlight that BESMOD only is a container, so it is only as good as the component libraries it's built upon and the community of users. We have currently a really active user community at our institute. Over 20 students and 10 PhD students already used it. And personally, I do workshops currently because the documentation could be improved, but I plan to do YouTube tutorials as well. And yeah, if you're interested in using it, feel free to visit the repository, use it and ask questions. I'm really happy, as long as the documentation is not ready, to give personal workshops as well in my time. So thanks for attending my presentation, and I'm really happy to answer any questions you have.
Thanks for the nice presentation. And then one question of how you into or what's your approach here about the compatibility between the controls and the HVAC system. For example, in the HVAC system, a simple example would be the outdoor air intake where you may have an economizer that has 3 dampers, or you may have a heat and power unit. So if you have 3 dampers, you have 3 control signals. If you have a heat and power unit, you only have 1 control signal. And the controllers are associated with it. So how do you make sure that once you switch out, for example, input that the control that is at different hierarchical level is consistent and compatible with that system?
Actually, trial and error. So I guess you came in after the slide where I mentioned that I use expandable bus connectors. If two systems are not working together because some bus connector is missing a value, then you will get an error message that there's missing a value. Currently, we don't have any selection that Daimler, for example, automatically checks, okay, this system needs these inputs in the bus, and so it doesn't change it, show it in the choices for matching. But it would be, I guess, a really easy to implement web interface to just check which bus connectors are used and then only show the really matching one.
Okay, yeah, let's chat about the written models. We have some work going on in that could be allowed to do offline.
Yeah, we will do things.
I have one. So on platforms, I think tested the library and we have selected issues when using it on
We have tested it on Daimler currently, and we also tested the compatibility to Modelica. There are currently 3 issues in Modelica. You can't use arrays in expandable connectors, you can't use expandable connectors in expandable connectors, and there are issues with replaceable array definitions. But if you avoid modules which use these concepts, then you can simulate in Modelica. However, I didn't compare the simulation quality. Yeah. Thanks.
Hello everyone, good afternoon. I'm Casper from Northern Berkeley National Lab, and here today I'm to present our company's paper with the title Fan and Compute Efficiency in Modelica based on the Euler number. This work was supported by Carbon Energy and emerged from my project one. But a little bit of a background to start with. When we talk about fan efficiency, it's defined as the ratio between the flow work. It's defined as the ratio of the flow work, the ratio of flow work and electric power consumed. And the flow work is the product of flow rate and pressure. Any work that's not used to generate this pressure to generate this work is not useful to us, as we have this definition of efficiency. But often we don't have enough information for the pump or fan, or very often we don't have a preliminary concept of the system, so we have to assume that the efficiency is constant. In such a case, when the flow rate approaches 0, then we have the power consumption also approaching 0. Unfortunately, this is not correct. If we look at the power map up there, the fan will have static pressure over flow rate, and somewhere in there we can see a 2 horsepower line that's crossing both the axis with 0 flow and the axis of 0 pressure. So we have either 0 flow or 0 pressure, but the fan is still consuming power. In this case, it's not the efficiency it's not the power that's going to 0. We have a positive power. When the flow goes to 0, this fan is basically doing nothing useful, but still consuming power. So it's power that is going to 0. This is especially important to us when we have a scenario where we have a slow flow rate, but the fan is controlled to maintain a certain level of pressure, which is very typical for VA systems. So in this figure here, we have power versus flow. In the DO2 model, with BSD, when the flow rate approaches 0, we can see that the model output states the power will also go to 0. But the measured data says otherwise. The measured power is not approaching 0, it's going to cross the axis with a positive value. So this is what motivated our work. In a typical simulation program, we often simplify the functional dependency of power over both flow rate and pressure to just a simply a dependency of flow rate. Usually it's because it's difficult to compute power in simulation programs. It tends to form algebraic loops. For example, in active standard 9.1, we have this curve here that uses the power ratio to have this functional dependency of power over flow rate directly. It doesn't exactly cross zero, but it's essentially zero if you look at the formula closely. There are two problems with this. First, we don't want to cross zero, as we discussed. Secondly, because it eliminated the dependency between power and between the flow rate and pressure. So we are here explicitly making assumptions about the system curve. So in Building's library, we are implementing a new method of computation with this thing called the Euler number. So what is Euler number? First of all, the Euler number is defined as the ratio of pressure forces over inertial forces. So we manipulate this thing a little bit, then we end up with an expression with pressure, area, density, and flow rate. And in the literature, we didn't create this method. We're implementing a method invented by other people to Building's library, and with the authors used a modified Euler number, basically removing all the constants in there. So when we end up with a dependency of pressure, diameter, density, and flow rate. And they showed that with different types of pumps, different types of fans, different sizes of fans and different operational regions, the measured data of the fans all follow this correlation curve very, very well. So this curve is a functional dependency between the ratio of fan efficiency and the ratio of Euler number. So the y in this function is efficiency at any operating point over the peak efficiency. And on the x-axis, we have the Euler number over Euler number at the peak point. And the peak point is the point where this fan operates at its maximum efficiency. And since it's the ratio of the Euler number we're concerned with, in the end, the user only needs to put in one data point of efficiency, pressure, and flow rate. With that, we're able to estimate the efficiency at any operating point. Just to look at what this function looks like, so it's this monstrosity. The independent variable is hidden inside Z2, and we can see that for Z2 we have cos error function, we have a sine function here, 0,2 over 0,2 absolute value. So this function is computationally expensive and not globally differentiable. We'll talk about how we handle that in a couple of moments. And also, the original authors only applied this to fans, but remember the Euler number is not defined with any thought about what medium it is. And in the Building's library, we handle fans and pumps the same. They're the same model. So there's no reason, I think there's no reason it doesn't apply to pumps as well. And we did test the data we have for pumps and plotted it against this curve. So the pump data also follow this curve pretty well. So we think it should be also applicable to pumps. So model implementation, we implemented this model in the Modelica Buildings library, which is a free open source library with dynamic simulation models for building energy and control systems. Currently, it's still on the develop branch. If you look at the issue post 2668, you should have the information to check out the branch and look at this model. So finally, the fan efficiency in Buildings library is broken down to two components. One of them is the hydraulic efficiency. It corresponds to the hydraulic work, and we'll also see the terms shaft work or brake horsepower. This is the efficiency that this correlation function is applicable to. Another component in the efficiency, the motor efficiency, this is beyond the scope of this discussion, is otherwise handled in the model. But most of the cases, motor efficiency is constant enough that we don't really need to worry about it. If we multiply these two efficiencies together, we get the total efficiency of the fan. And we implemented this correlation function as two lookup tables using the block from Modelica standard library, the computable 2DS, for three reasons. First, we avoid directly evaluating that huge chunk of function all the time. Second, we can avoid log 0 over 0 more easily in certain parts of that function. And thirdly, we can avoid 0 over 0 more easily in this definition function of power when both flow rate and efficiency approach 0. And let's talk about validation. So we tested, put some data to test, and we will talk about our data sets, and we'll look at one fan in particular. The validation is very simple. So we have this fan of pump data, the power map here. We try our best to find the point where efficiency is the highest, and we see if we can reproduce the power lines on this map. So what we do is we first find the line with the maximum speed on this figure. We find the point on this line with the highest efficiency, and we see if we can reproduce the values of power on this line. So for one fan in particular, we have this results figure, have efficiency over flow rate and pressure, then power over flow rate and pressure. And we have two lines in these graphs, in these figures. We have one line that represents the interpolated data we found from the power maps, and one line with the model output using the Euler number method. So looking at the first two figures, we mainly just see one line, so which is very good news to us. This means the efficiency computation was very successful, capturing the actual values we found from the power maps. And the next two figures are powers. For the majority of the range, we can see that also the two lines are very, very close to each other. We'll see some discrepancies at high flow rate and low pressure, and we'll discuss this region in a little bit. We also plotted a few lines to represent what would happen if we assumed constant efficiency. So the lower line in those two boxes, the 0.68, is peak efficiency, peak hydraulic efficiency of this fan. So if we always assumed peak efficiency, obviously we're going to always underestimate power consumption. And if we assume slightly smaller value, 0.46, roughly 2/3 of the peak efficiency, then we're going to end up with underestimation in some region and overestimation in some other region, which is very similar to what we see here at the beginning of the presentation. At low flow rates, the estimation is underestimating power, and at higher speed, the model was overestimating power. We also plotted the error distributions for all the data we have. So the error here is defined as computed minus interpolated over interpolated. So we used 18 sets of pump data and 7 sets of fan data. Here in the error charts, we have errors for the efficiency, also over the versus flow rate and versus pressure, and also errors for power versus flow rate and versus pressure. The first thing I saw when I plotted this out was that the skewness of each box whisker plot were very, very consistent. So if we just look at the error charts for efficiency, we can see that except for one box, all of them are skewed to the negative side. And for both, if we just all of these boxes are skewed to the negative side on these charts. And I think that's because, so we were consistently underestimating efficiency. And I think the reason is that we weren't very smart about looking for the peak efficiency on this power map of the fan. As I mentioned, we tried to find the peak efficiency along the line of the maximum speed we found on this map, but probably the actual global peak efficiency appeared somewhere even higher, as in a region that this fan is not intended to run at, but the peak efficiency is hidden somewhere there. So because we're underestimating the peak efficiency, and the efficiency we computed at any operating point which is based on that point, were all consistently underestimated. And because power is related to the reverse of efficiency, the power, the skewness of these box plots are all in the positive side. But other than that, if we draw a 15% line on power, then we see that for a very large range of flow rate and power, we all fall within this 15% of error range for the majority of the data, so which is very promising. Let's also look at validation at reduced speed for these fans. For this one particular fan we plotted, we made very similar plots for power to look at different speeds. And first, we can see that the error behavior at different speeds are very, very similar. But we see that we have consistent errors at certain regions, which is at this region when we have high flow rates and low pressure. And in this region, we have increased errors. But maybe this region is not too important to us. If we look at this other figure with static pressure versus flow rate, which is a different fan, we have two important points here. One is the flow power point, which is the point where the fan achieves maximum flow rate while maintaining the required pressure. So in operation, the fan is not supposed to go anywhere to the right of this point. We also have another point on this plot, which is the purge point, which is only achieved when all the VAV boxes are fully open. So physically, this fan cannot go anywhere further to the right of this point. Therefore, if we have this lower right region that this fan is never going to, we're seeing, therefore, having error in this region is not very important for the type of applications that motivated this study. Let's also look at a quick discussion. If we can actually rearrange the correlation function in a way that in the end we can see that efficiency is actually going to stay constant along any line that fits this expression. So this expression looks terribly like a constant characteristic curve, the system curve. So this model, unfortunately, is not magic. It does not reproduce efficiency degradation along any constant system curves. But fortunate for us in the United States, this is in line with the simplification often used by fan and pump manufacturers, which is explicitly permitted by ASHRAE standard 51. So what this means is that if we look at this fan power map, it kind of claims it tested multiple speeds, but it actually only tested one of them. All the other curves are just scaled down. We pull down, we read this chart and tested them that if we find any curve that's a constant system curve, the efficiency on these points are all the same. So it looks like they tested a lot, but not really. So then, therefore, for us, it is safe to say that this implemented method has the same accuracy as using manufacturer data you found in basically this country. We have one more example here. We tested it on many large models. It's just a very quick comparison of the model we had with regard to efficiency of the fan and the pump actually, and the power consumption of the pump. So this pump in this model operated along this line here. And if we use the old model where we assume constant efficiency of 0.49, so 0.7 of hydraulic efficiency times 0.7 of motor efficiency, then we have a much lower power consumption computed from this model. But if we use the new method where we have variable efficiency for both the hydraulic and motor efficiency, then we end up about a much larger number for power consumption. So this modification, this method certainly has potentially have large impact on your models, any large-scale models you might be building. So to sum up, the implemented method uses the Euler number and the correlation function to estimate the whole power and efficiency map of any pump or fan. It only needs the user to provide one data point at the peak efficiency, and the computed power does not go to zero when the flow rate approaches zero, which is important for the type of application we're looking at. At the nominal speed, the computed power of the sample had errors within 15% for a very large range of flow rates and pressure. And the accuracy, although the accuracy drops considerably at low pressure and high flow rates, this type of operating point is not very usual for the type of application we're looking at. Otherwise, it has the same level of accuracy as using simplified manufacturer data. And thank you very much for your attention.
Yes.
For all fans, like roll fans also?
This is a question you have to unfortunately ask the original authors. They did test, they claim to have tested different types of fans, but we don't know because it's not a formal publication where we found the first use of this method. So they don't have a formal documentation of what types of fans, what sizes they actually tested. This is all from Energy Plus engineering reference.
Not speaking to functional sense, that confident on the develop itself, I think we just about they need to explain that that not how I do and develop itself. Okay, I thought, yeah. So, we go to the here, it says the power of macro is the effort is this way you might be correct, but in measuring we have very much the heat gain, which is added to the effort, would increase the air temperature, so some pressure and you would bring the coffee.
Yes, that's right. In the actual model, we do regularize the power to let it go to zero at very, very low, speed or very, very low flow. But I don't remember that on top of my mind. But yes, we do let the fan actually be turned off when it's supposed to be turned off. I don't know, to be honest, but it's well, we were trying to find some way to find a good boundary, but yeah, whether 15% is a good number is up to discussion, to be honest. Yeah, we have the data from manufacturers. Sorry? I'm sorry, what do you mean by best accuracy? No, 15% is the, if we go back to the box whisker plots, so 15% within, 15% is where the whisker of the box whisker plots touches that 15%. So it basically means excluding the outliers, all of the data, everything, all the data set, all the data we have fell within 15%. So it's not the interquartile range, it goes to the whiskers. When you don't have outliers, then that's all the data.
Maybe another question. Is it possible for manufacturers to measure the actual point of flexible efficiency? Because that the real point would be somewhere outside the curve. So instead of measuring along the curve, they would have to just measure one point.
When I was looking for data, I asked some former colleagues who work for municipal water supply company, and they told me it's very expensive. The manufacturers told them it's very expensive to do measurements with the pump. So when they requested more detailed data, they were refused or be sent to the field. So I imagine there's either it's actually expensive, cost prohibitive, or it's just difficult to request such data. But I think that's going to be very valuable.
Thank you.
Thank you very much.
Our last presentation is from Jianqin Ma, and he will be presenting on transient simulation of an air source heat pump, recycling, frosting, and recycling, defrosting.
Good. Thank you. And good afternoon. This work was authored with
Dr. Donatin and LDL and my advisor, Dr. Jim Bryan to do. So in this work, it's about a simulation study for air source heat pump incorporating frosting and defrosting operations, and also tested a residential heat pump in the lab for other applications. It's followed by conclusions from the current work. So frost accumulation is a common phenomenon for climate heat pump, and a periodic system needs defrost to return to its operating characteristics. And really, the operating nature of cold climate heat pump is this cycling operation between frosting and defrosting. And to model this process is kind of challenging because you have the couple of dynamics of refrigerant to frost to defrost. So the goal of this work is to can meet a gap in the literature that there is no general simulation tool that can handle the cycling behavior of frosting and defrosting. And we did a quick literature screening that most of the studies only focus on heat exchanger, either under frosting or defrosting. And there's a very limited number of rigorous studies on system level simulation. And in terms of considering the flow reversal and also we found that after incorporating frost formation and the frost melting, the model is kind of getting very complicated. So we also improved some component models for robustness. And let's first look at the heat exchanger. We applied a staggered grid for discretization of governing convection equations, mass, moment, and energy. And here I just want to point out because this work deals with reverse flow, which will be very helpful when we use any empirical correlations for friction factor or heat transfer coefficients. Because typically those correlations are derived at a steady state, but when you have mass flow goes to zero, there could be singularity. So following the Modelica standard library, for example, for the friction factor, we can apply the modified friction factor to avoid that singularity. And also, because friction is in the opposite direction to flow direction, so we apply a sign function for the friction report. And for the metal structure, we assume a uniform temperature of tube and its associated things, length, lambda patterns, energy balance. And for the airflow, because this is a frost flow configuration, so we assume quasi-steady state, then we can derive the temperature and humidity profile. And please notice this is only used for forced convection when the fan is running. During defrost, the outdoor fan is off. So there's another set of equations for natural convection so that we can avoid the singularity when air flow is close to zero. And so far, this is the heat exchanger model that we use for non-frosting conditions. But in this work, we integrated a detailed frost formation and frost melting model into each control volume to kind of investigate the impact of frost on system performance. For frost formation, we consider one-dimensional that the mass transfer from moist air can be consists of two parts. So portion of the mass transfer will deposit on the frosted surface, which contributes to the thickness increase, and then another portion will diffuse into the frosted layer to increase its density. And in order to solve these two mass flux, we form the mass and the diffusion equation within the frosted layer. Those equations just apply boundary conditions at the frosted surface and the base layer. Because when we derive these equations, we neglect the energy storage, so it's actually a quasi-steady state analysis. So we update the frost density and thickness after a fixed time period. You can consider this as a discrete system. But later we will see that we want to have a consistent model structure where density and thickness are state variables for a frost layer, either at frost formation or melting. So apply the first order filter that from the frost formation model, you are calculating the reference values, and then the actual state variables are tracking those reference values. And then in terms of frost melting, we apply multi-stage forced melting process from the literature. I will not go into detail, but we can also form a state vector that includes thickness and temperature of different layers. But the problem is that because it's a multi-stage forced melting process, it is described by a case-by-case mathematical distribution, which means you need to switch between different types of governing equations when the frost melting can progress. From a computational point of view, this is not efficient because of using the if and then rules. These are discontinuous, and you are generating too many events during the online simulation. So to improve this model, we applied a fuzzy modeling based approach that we are running all the governing equations from all the stages simultaneously, but just obtain a weighted combination of them based on some linguistic variables. And this is the final heat exchanger model for all the report. That as the primary heat transfer direction, we have 4 elements for each chemical volume. We add a frost layer so that we can run frost formation and melting model simultaneously, but we just interpolate their dynamics based on the operating mode of the heat pump system. So the switching variable, you can either use the operating mode of the heat pump or reversing valve opening. It's just an input to the cycle model. And then to form the cycle model, compressor and experimental models, we are using the performance map-based models. Then the outdoor fan, we are using a banker, which is responding, kind of responding to the frost accumulation. So when you have more frost, it blocks air, then you got more pressure drop across the coil. Then according to a banker, the mass flow will be small. And then for the accumulator, we assume refrigerant inside is saturated, so that you can form mass and energy conservation. And the outlet refrigerant from the accumulator is also saturated with her. The last component is essential to have a reversing valve model. This is how we can trigger flow reversal. So following the literature, we use a system of check valves to control the flow direction. For each port of the reversing valve, there are 2 check valves that can control the flow direction. One is on, another is off. If the on-off status of them are switched, then you reverse it. And we also tested a commercially available heat pump unit. It's commercially available, which means we don't have access to internal control. But for model validation, that's good enough. We just need to collect the data. It was installed in a pair of measuring chambers, and we have refrigerant pressure and temperature measurements at those locations. This is the test that we did. So it's spanning 3 hours, and from the compressor speed, we can see that after it starts up, at 30 minutes, it switched to the first defrost cycle. For this specific system, it never shut down. During defrost, it just running at a lower speed. And then it goes through 2-hour heating period, then switch to the second defrost cycle. So if our model can capture this complicated dynamics and there are multiple cycles of heating and defrosting, then it demonstrates the model's capability for the objective. This is the result that we compare the discharge and suction pressures. We can see that for discharge pressure, when you switch to defrost cycle, there's a very fast pressure equalization process because EX phase fully open. And when the system is operating at the second heating cycle, which spans 2 hours, we can see after about 100 minutes, we observe a system performance degradation because discharge pressure is decreasing. You lost heating capacity to the indoor environment. This is because we lost heat transfer in the outdoor environment. We see that zoom-in figure that there is a slight decrease of the suction pressure. But for this system, it turns out the discharge pressure is more sensitive to property change at the suction side. Then after 2 hours, the system switched to the second defrost cycle. So the first defrost cycle lasted about 5 minutes, the second is 10 minutes, then system switched to the third heating cycle. And we can see the model can basically capture all these complicated dynamics. We can also look at on the left is the refrigerant mass flow prediction and measurement on the liquid line. But please notice for the mass flow meter, there's a configured measurement direction, which in this case is a heating mode. So when the system switch to defrost cycle, the output signal from the flow meter just saturate to 0, which means we don't have measurement of refrigerant mass flow during defrost cycle, but the model can predict that. But that's okay, because the indoor fan is always running, so we can validate the indoor heating capacity. We can see that during defrost cycle, of course, the heating capacity goes to negative because you are taking heat from the indoor environment, and we can also validate the capacity power. These metrics are pretty good. Then we can, because we have detailed frost model, we can predict the frost properties, the thickness and density here for selected control volumes. So CV1 means the first control volume, which is close to EXP at the inlet of temperature, and CV30 is close to the compressor, is the outlet. And then we can also predict the outer core airflow passage, the area that for this 2-hour frosting period, 20% of airflow area was brought due to frost accumulation. Topics are typically difficult to measure at system level, but the model can provide us an insight on the physical behavior. And also, for the non-uniform frost formation during that 2-hour heating period, our model can also provide an insight about the non-uniform frost accumulation. We can see that more frost tends to accumulate at the inlet of the heat exchanger, but the frost close to the outlet tends to have higher density. And using the model, we can evaluate the defrost performance of this different unit, that we can evaluate the defrost efficiency. So we need to predict the total amount of frost accumulation. Then the efficiency is defined as the heat that is supplied to melt all the frost and vaporize the returned water over all the energy input to the system. Here we also include the heat transfer from the indoor environment to penalize defrost cycle, because you are taking heat from indoor, which could cause some of these problems. And for this test, the results are the first defrost cycle has 30% efficiency. The second one has 56, has higher efficiency because there's significantly more frost accumulated for the second cycle. The conclusion is that we develop and experimentally validate a dynamic modeling framework for air source heat pump, and the recycling operation of frosting and defrosting. And for this system, the simulation speed is the real-time factor is close to 0.5, which means the model can run 2 times faster than real time. It is okay for simulation, but for control and fault detection applications, it's still challenging. So more work could be done for the simulation speed. How much do you have?
Yeah, maybe a couple of things.
Okay, I just have a couple of complementary slides. That I want to briefly introduce the fan model. That in order to model non-uniform frost accumulation, you need to have a fan model that is interactive to frost accumulation of the outer core. Now the problem is that I established a hydraulic equilibrium between the fan and the outer core to solve for the mass flow rate. So the pressure rise of the fan is equal to pressure drop of the core. But the problem is, what is this intermediate pressure? In order to obtain this value, we need to solve a algebraic equation system where we have the pressure equalization and also the mass balance of the fan. That means at every time step, this algebra loop needs to be solved. So this is kind of challenging for computational speed and also the cost of the whole system because you need to do iterations. Question is that we implemented a new modeling approach, the robust sum fluid formulation. I believe that the author will be here for a workshop on Friday. The idea is that you convert this algebraic system into an ODE system by adding dynamics to all the mass fluids. So at every time step, all the mass fluids are state variables, which means they are known. Then you can solve for all the pressures explicitly on the object. So we avoid that algebra loop, but now it's adding an ODE system. With that, I welcome my questions. Thank you.